Okay, in our last video, we walked through balancing and putting everything together, predicting our products and determining what the initial molarity was of one of our reactants and determining what the molarity was of our final product. So now let's look at our ionic equations. And the way we need to do that is using the tool that we came up with at the last video, and that was establishing what the charges on everything are. So I come here, and remember this is going to be 3 plus, and this is minus 1, and this is 2 plus, and 2 minus, and 3 plus, and 2 minus, and 2 plus, and minus 1. And I'm doing that because in order to go into my ionic equations, I need to know what my charges are. So I can write those appropriately. Your ionic equation should always include the charges of your ions and the quantity. So the first thing I want to look at is here, I've given you that all of these species are aqueous. So for something to be aqueous means that it is in its ionic form in solution. We will not be breaking ever anything up if it were a solid. So we have no solids here. So everything is going to be in its ionic piece. So let's look here. First I have 2 aluminums, so 2Al, 3 plus, aqueous, plus, well, I have 2 6 hydroxides, so 6OH minus, aqueous, plus 3 bariums, so 3Ba2 plus, aqueous, plus 3 sulfates, 3SO4 2 minus, aqueous, and that's going to go to 1 Al 3 plus, aqueous, plus 3 SS 3 SO4 2 minus, aqueous, plus 3 bariums, so 3 Ba2 plus, plus 6 OH minus, aqueous, aqueous. Cool. So everything now is in its ionic form. And after we went through and wrote out that molecular equation and determined all of those wonderful physical quantities of things that we have, now I say, well, did we have a reaction? And the one thing that we look at for our spectator ions are ions that appear on both sides. So I come through here, I have 2 aluminums, oops, 2 aluminums, drop to 2. 2 aluminums here, 2 aluminums here. So that's a spectator. And over here I have 6 hydroxides, 6 hydroxides. That's a spectator. 3 bariums, 3 bariums, spectator, spectator. 3 sulfates, 3 sulfates, spectator, spectator. And now let's go ahead and write what we have left, which is nothing. Absolutely zip, zilch, nada. Otherwise known as no reaction. Done. That is my net ionic equation. No reaction. There's nothing. Everything is a spectator. So one of the things that you can key in on is if you are given things with their phase labels, if everything is aqueous, we don't actually have a darn thing going on in our chemical reaction. We have everything is just hanging out in their ionic form, happy as a clam, doing nothing. Absolutely Nada. Zip, zilch, zero. So all aqueous, you can jump to no reaction. If you're asked for the net, if you're asked for the total ionic, this is the process you need to go through without the crossing outs. Okay? Now, one of the things that I did want to go over, because then this is like, well, we're done. That's not very exciting. Is looking at the concentration of ions that we have in this solution. Well, we determined that I have, from the previous reaction, let's see, I knew it, that we have 0.00675 moles of BaSO4. If I want to know how many moles of barium ions I have in the solution, specific to what I have put here, now I can use my mole to mole ratio. So each of these coefficients tells me how many moles of each of those ions I have, and they should be the same on both sides, because I can't magically produce barium ions without them existing in the first place. So let's use our stoichiometry. I have 3 moles of BaSO4 and 3 moles of barium, Ba2+. So that tells me that I have 0.0065 moles of barium, or Ba2+, and because this is also going to be the same thing, I have 3 moles of SO42- to 3 moles of BaSO4. Well, that's a 1-to-1 ratio, so I'm also going to have 0.065 or 0.00675 moles of barium sulfate. So when we figured out the molarity of the barium sulfate, that means also that I have 0.225 molar barium ions in the solution, and I have 0.225 molar SO4. So that's not the same for my hydroxide, or my aluminum hydroxide. So let's see what that comes out to be. Did I already calculate that? I don't think I did. So we'll just do it from scratch. That I have 15 milliliters of AlOH3 times 0.30 moles of AlOH3 to 1,000 milliliters. There's my molarity piece. So that gives me the moles of AlOH3. Now, if I want to know what the concentration of each is, first I need to find out the moles of each. So in this one, I have, times my stoichiometric coefficients, 2 moles of AlOH3, it's just from the coefficient, for every one of those moles, I have 3 moles of hydroxide. So I have 6 moles of the hydroxide. So 6 moles of OH minus. So this would give me the concentration of hydroxide ions. And so one of the things you might have gone on to, I keep sliding back to just the concentration of each ions in this molecule, and that's because this simplifies down. So if I divide 2 into both of this becomes 1, and that becomes 3. So I'm jumping right to mentally the ratio of, for every 1 mole of aluminum hydroxide, there's 3 moles of OH minus. That same thing comes out here. So now to get my molar concentration of that, I had to put that in my calculator. So 15 times 0.3 times 3 divided by 123 gives me 0.0135 moles of OH minus. And now I could ask two things. I could say, what is the molarity of hydroxide ions initially, so just in that 15 mils? Or what is the final concentration of hydroxide ions after everything is mixed together? So let's do the final. So I have 0.0135 moles of OH minus per, well, I'm combining those two solutions, so per 45 milliliters, and now turn that into liters. There are 1,000 milliliters in 1 liter solution. So 0.035 divided by my 45 mils times 1,000 milliliters gives me 0.3 molar OH minus. Another way you will see that written is that the concentration, these brackets mean concentration of OH minus, is 0.3 molar. You can see it written both ways. And we can do that for everything if we wanted. We can check out the concentration of aluminum. Did I already do that? Kind of forgotten. Did OH minus. So we did our moles of BaSO4, so we've already played with those. Play with that. So just to rehash, take the thing that you know that you actually have. So this is going to be the thing that you put together in the lab, that 0.30 molar and the 15 mils. That tells you physically what you have. The mole ratios of everything, all of these coefficients here, tell me, using stoichiometry, what do I actually have in this solution based on the stoichiometry. So here's the physical quantity I came up with in the last video, given all of the volumes mixed together. Here's my mole to mole ratio. And then here's doing the same thing again. So from the stoichiometry, from what I actually used in the lab. And there you have it.